Okay, good evening again. Good morning. This is Professor David J. Delos Reyes. It's August 26, 2023. The time is 1:17 a.m. Okay, my long video format discussion for this session will be alternating current circuit, and this will now be lesson number 31. The title of the topic is Example Problems on the application of delta to y transformation, delta to y. Without knowing the transformation delta to y, we could not solve this given problem. So I will try to give you an example problem so we could visualize the importance of the so-called delta to y transformation. Okay, let's proceed. So this will now be lesson number 31, alternating current circuit, lesson number 31. The title of the topic is Example of delta to y transformation. Delta to y transformation meaning without using this transformation, we could not solve the given problem. I think it's impossible to solve the problem without knowing the transformation. Okay, let's proceed. I will give you an alternating current circuit. It was actually same circuit from the previous lesson number 30. Okay, but now I will be giving values, and the problem is asking what will be the current drawn from the circuit. What will be the magnitude of the current drawn from the circuit? And we are given 6 impedances: Z1, Z2, C3, C4, C5, and C sub 6. For the meantime, forget the the impedances in the blue markings, because later on I will discuss this is not included for the meantime, so assume that this is not yet there, okay? Because when we will go with the so-called delta transformation, I will be drawing this one. I draw it now, but initially this was not in the diagram, okay? The given values are these: Z1 10 angle 0, Z2 is 8 angle 75 degrees, C3 is 20 angle 45 degrees, okay? Z4 is 15 angle 30 degrees, Z5 is 12 angle 60, C sub 6 is 9 angle negative 45 degrees. So this should be capacitive load. All the previous loads were inductive. And the applied voltage is 440 volts, angle 0 degrees. The problem is asking what will be the total current, okay, total current drawn by the 6 impedances, okay, using the delta to y transformation. Okay? If we try to visualize the given circuit, okay, without this top portion here, and for the meantime forget the blue markings, okay, it is an AC circuit. But since our professor is a terror, he added one impedance over here and connected it over here. So the ordinary solution, series parallel solution, for the meantime we could not use it, okay? So the only way to simplify this one, for it to become, or for us to use the series parallel concept, is by using the so-called delta to y transformation. Meaning to say, we must have to, this C3 here, C5, and C4 actually in the orientation delta. They are in the orientation delta. Okay? So if they are in the orientation delta, we could draw an impedance inside with a letter T. This one now, the one in blue. Okay? This point here is connected here, connected here. So actually this point here are this. Right? So I will now be presenting or representing another impedance in the circuit, okay, to be C sub A, this is C sub B, and C sub C. the original configuration of C3, C4, and C5 is actually delta. So for us to bring out the solution by using this series parallel concept, we must have to eliminate this one, eliminate this one, and eliminate this one, and bring out C sub A, bring out C sub B, and bring out C sub C, because actually we could calculate for those values, right? So if I will try to replace C3, C4, and C5 by these three here, okay, it was by using the concept the last time around, the previous lesson. So if I will try to replace C3, C4, and C5 now, actually I could erase it now. I will try to erase. Okay, I will try to erase this one. Then I will try to erase this one. Okay, so that's now the configuration after transforming the three original impedances, which are in delta. C1, C2, C, this is actually C3. This is C4. This is C5. Is it C5? Yeah, C5. Okay. So after transforming the original delta to Y now, this will not be the configuration. It is much simpler now because by inspecting this C1 and ZB are in parallel or are in series. Okay, they are in series. This portion here and this portion are in series, and C sub 2 and C sub A is also in series. C sub 2 and C sub A are also in series, right? And C sub C and C sub 6, okay, are also in series, right? But if we try to compare C1, CB, and C2, CA, okay, I will go here. They are in parallel. Okay, they are in parallel. So the single equivalent of this is now connected in series with this. So this is now a series connection. Okay, series. That's the one I'm telling you. Without using the delta to Y transformation, we could not use the so-called series parallel concepts. But after the transformation, we could see that Z1 and CB are in series, C2 and CA are in series, right? And the combination of these two here is in series with the series combination of C6 or C sub C and C sub 6. Okay, so by just following that format, we could bring out the quant. What's the relevance of this? We are going to solve for the total impedance first, right? By compressing these values, C1, CB, C2, CA, and C sub C, C sub 6, into one single impedance, okay? If we got the total impedance, we will divide the voltage by the total impedance, okay? And we could compute for the total current. Okay, so that's the summary of the solution. So, okay. So to start the solution, just change C3, C4, C5 to rectangular. We will take the summation. Okay, the summation, the single equivalent is 46.1, angle 44.02 degrees. What's the relevance of this? The relevance of the summation here, the summation of C3, C4, and C5, C3, C4, and C5, the one we remove here, okay? The one which are original delta. We take the summation, so the value of this one, because in the formula on how to compute for C sub A, okay, it should be C3, C4, the adjacent, the product of the two adjacent, plus the summation, okay? So we could now actually compute for C sub A, the Y equivalent. C sub A is the product C3, C4 all over the summation, right? The summation. This was given the last time around for converting delta to Y. So if we try to substitute values, okay, then compute for C sub A. This is just a mere substitution, but be careful with your, what you call this, polar to rectangular conversions, okay? One mistake, it's all wrong. And the value of C sub A is actually the magnitude, 6.5, okay? The angle is 30.98 degrees. So we now know C sub A. We now know the value of this one, right? And for C sub B, where's C sub B? C sub B is here. The adjacent impedance of this in the delta is actually C3, C5, right? C3, C5, all over the summation. It is just a mere substitution now. We could compute for C sub B, and the magnitude of C sub B is 5.2. So we now know C sub B, the value here. For C sub C, this one, the adjacent impedances considering the delta is C4, C5. Okay? So C sub C is actually C4, C5 all over the summation. Okay? So it is just a mere substitution now by using your, what you call this calculator. What comes out for the value of C sub C is 3.9. So actually, we are now given the value of this. We are now given the value of this. And we are now given the value of this. The formula we use is for the so-called conversion from delta to y, which is the product of the adjacent over the summation, product of the adjacent over summation, product of the adjacent over summation. Okay, so that is just a procedure. There's no hard thing about it, but the only problem is your accuracy. Okay, let's now try to compress C sub 1 and C sub B. Hold on. I will be getting my erase. I will erase some portions so it will be understandable. Okay. C sub 1 and C sub B are in series, right? So we take the sum. This is the magnitude. They are in series, right? This one and this portion. And C2 and C sub A are also in series. Substituting values, the magnitude is 13.453. This one, the single equivalent of this. And if we try to take the sum of C sub 6 and C sub C, C sub 6 and C sub C, this is the rectangular equivalent. Okay, we do not need the polar for this one. Okay, and what's next? Okay, the simplified impedances, okay, after the conversion from delta to y is this one. So this is C1 CB, C2 CA, and C sub 6 CA. So we will now try to compress these two here. They are in parallel. So it should be the product all over the sum, right? 1 over z will be equal to 1 over x plus 1 over y. If we try to convert this, z will be equal to the product xy over x plus y. Okay? We will be using this formula. So C total now, if we try to combine this one into 1, it will be the product all over the sum. Okay? This portion here is this. Right? So it is just a mere substitution now. Because we computed, our solution was very systematic. We computed these individual values separately. So when we go to the total impedance will be the single equivalent of this. The product all over the sum. Right? This is the sum, this is the product. And the last part is C sub 6 plus C sub C. Because this single combination here is in series with this. So this is plus, right? So substituting values and simplifying it, what comes out for the total impedance is 14.659. The angle is 2.83 degrees. So we compress this one into 1, and the compressed value is in series with this. So after adding it vectorially, the magnitude is 14.659. These values are just mere substitution now because we computed the values separately, okay? We just take the values, we put it here. So the total current now, by using the equation voltage equal to IC, current now will be voltage over impedance, right? 440 angle 0 degree, right? Am I still in camera? The total impedance as per our computation, okay, which was very long, and it was really came out by using the delta to Y transformation and the concepts of series parallel concepts. Okay, what's come out is this value here. So we divide 440 by that value. Okay, what comes out is 30.016. 0 minus 2.83, it will go up. The angle is negative 2.83 degrees amperes. So the total current drawn by the original six impedances, okay, is actually 30.016. The angle is negative 2.83 degree amperes. Okay, that's the solution. There is no other solution to bring out the current without knowing the delta to Y transformation. So that's the importance of the so-called delta to Y transformation. Without knowing it, we could not solve this one, theoretically or on the board or by using your paperwork, you know. So delta to Y transformation is very important. We converted the original delta here to Y. So after converting it, it becomes simpler now. It was just like that. Okay? This one is in series with this. This one is in series with this. These four combinations here is in parallel, right? And this the parallel single equivalent is in series with this one. Okay? So after combining it, the total impedance is 14.65 angle 2.83. And since we are given the total impedance, the total current will be total applied voltage of the source divided by the single equivalent impedance of this, which was a complicated solution. That is 14.659 angle 2.83 degrees. So the total current is 30.016 negative 2.83 degrees. Okay, that's it, guys. So for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share. Okay, try to watch my long video format discussion on alternating current circuit. I am assuring you, you will learn something from it. Okay, good morning from Los Angeles, Professor David J. Delos Reyes.